Okay, to begin talking about simple harmonic motion, or SHM, we're going to be talking about motion, so there is going to be references to a new set of kinematic equations and variables and all that sorts. Um, when something is simple harmonic motion, it is oscillating back and forth. So you remove it from its natural position, and because it wants to return back to its natural length, there's a force acting on it. The force acting on it stops acting on it when it's back at its natural length. But because of the momentum of its mass, usually if the spring is attached to an object, the momentum of the mass is going to pass it past its natural state, and then it's going to push back, trying to get back to its natural state right there, trying to get back to its natural state that the momentum has made it miss, and then it's just going to go and pass it, and it's just going to be this long repeating pattern over and over again. So if you imagine the ball or the object that is oscillating being drawn on a paper that is moving upwards at a constant speed, you would get a nice sinusoidal wave where you have an amplitude and a frequency and some time, and we'll get into all that later. The distance, the wavelength of the sine function, or the distance from the crest to crest or trough to trough or equilibrium, or mainly the crest to crest or trough to trough, is called the oscillation region, which is also just commonly in the past been referred to as the wavelength. The x for our equations is 0 when it is in the equilibrium position. To keep that in mind. Okay, so let's look at all the equations. We're going to go through all the equations very quickly, and then as we go through the whole presentation, we're going to be using them and bringing them up one at a time. The first equation we already discussed is the force equation, which is the equilibrium equation, the force that's trying to return the spring back into its equilibrium, which is negative kx, and k is the force constant depending on the spring or elastic material. Because we're dealing in repeating patterns, we do have to talk about frequency. Frequency is equal to 1 over t, which is the period, or the period is 1 over the frequency. They're inverses of each other. Or negative, more specifically, they're negative reciprocals of each other. The next thing we're going to talk about is this. Now, we don't really have angular velocity anymore. We have something to deal with frequency. Now, to understand some of these equations, we have to look at a wave. To remember the wave, we have the wavelength or the oscillation length. This is your equilibrium position. If we imagine again, it's when the middle point where the object is trying to get back to. We have an amplitude, which is the distance from the equilibrium position to the highest point or the lowest point, and they're equal to each other, even though the picture obviously makes one look bigger than the other. And again, that's not angular velocity, it's technically angular frequency, but it's still measured in radians per second. One equation we have is also the max velocity. The max velocity of an object is equal to its angular frequency times its amplitude. And the angular velocity, that max velocity is in meters per second. Now, the maximum acceleration can also be calculated by finding the amplitude times the angular frequency squared. And both the maximum acceleration is going to be felt where the spring constant is experiencing the maximum force, which is at the crest and the trough. And the maximum velocity is going to be experienced at the equilibrium point. And we'll go into more of that. Now we have max acceleration because the spring force is constantly changing depending on how far away you are from the equilibrium position. There's going to be the acceleration is constantly changing. So there is such thing as a maximum acceleration. We have another equation that tells us that the period of a spring, meaning how long it takes for the pattern to repeat itself or how long to go from one wavelength to another, is equal to 2 pi times the square root of m over k, where m is the mass that is usually attached to the spring. Usually we assume that a spring is massless. If we simplify this, we can also say that the angular frequency is equal to k over m. And that particular equation is a combination of two. We also have the spring potential energy. Because the springs can hold energy, the amount of work it takes to stretch out a spring is going to be brought back. You can get that energy back. There's actually potential energy of elastic materials or spring, which we kind of derived before in the past, and it's 1/2 kx squared, where x is the distance from its natural length, and k is the force constant of the particular elastic material. We also have the typical mechanical energy. We know that mechanical energy is the total kinetic energy plus the total potential energy. Now, we have talked about two types of kinetic energy. We have linear L and angular kinetic energy, but because we also have potential energy of a spring, we also have two potential energies. We have the potential energy due to gravity and the potential energy of a spring. So if we write this down in an equation and break it up into the actual equations, we get this long equation to calculate the mechanical energy, a little bit more complicated than what we started off with a long time ago. We can use the mass times gravity times height equation because we're not really expecting huge drops. We're not expecting springs that are the length of the radius of the Earth or anything like that. So we won't necessarily need to use the negative g little m big M over r equation. But we could, and we would still get the same answer. It would just be a little bit harder. Okay, so these equations, these yellow markers you see on the screen are actually pointing out that the equations that are actually on your AP equation sheet. Your AP equation sheet does have the force of a spring, it does have the potential energy of a spring, it does have the relationship between period and frequency, it does have the period is equal to 2 pi over the angular frequency, and it also does have the spring period is equal to 2 pi the square root of m over k. Now that spring equation, there's another equation we're later going to do that deals with pendulums, but for the most part the S stands for springs. Plus you can also tell because it has that k value. That k value only really exists if we're dealing with springs. And we also have the potential energy due to gravity equation is also on your equation sheet, and the angular kinetic energy equation. And technically the kinetic energy equation is of linear value is also on there. And the 1/2 kx squared, which we already mentioned. And then here they are all together. All the equations in the bottom of your equation sheet, kind of nice and neatly collected together. We're also going to go over this one. This one's a little bit, we'll talk about this in a moment as well. Alright, we kind of already went over these in the last PowerPoint. If we look at the energy of the harmonic motion, meaning we're going to just simply derive that potential energy equation. When something, the potential energy equation on your equation sheet says that the potential energy of a spring is equal to 1/2 kx squared. Again, x is how far it is from equilibrium position. That was derived because the amount of work needed to stretch a string is actually going to be equal to the amount of potential energy in the string. And the work formula is force, the integral of force with respect to its position. Since the equation for the force needed to stretch a spring is equal to kx, we find the integral of that and we have 1/2 kx squared plus c, which is the change in how much work we've done. If we assume that we started at its equilibrium position, then pretty much the work done is equal to 1/2 kx squared. And now we missed the square there. And that's how they derive that equation, from the integral of the work needed to stretch the spring, which is equal to the energy that was put into the string, because a spring, the force of a spring is a non-conservative force, just like gravity is. If we look at this object that's oscillating back and forth, when we look at its direction on the wavelength, at its amplitude is when the object has the most potential energy. Now, when it's at its positive amplitude or negative amplitude, it doesn't matter because, again, the x is being squared, so it doesn't matter if it's to the right or to the left or up or down. When you calculate the potential energy of a spring, it's pretty much almost the absolute value of the displacement from its natural length. As we move down this green slope, the potential energy becomes kinetic energy. So the maximum kinetic energy of an object is when it's in its back, it's to its equilibrium position. From there, it starts to slow down and its kinetic energy becomes potential energy. then the potential energy becomes max, and the potential energy starts becoming kinetic energy, and the kinetic energy becomes potential energy, and just oscillates back and forth. At its amplitude is when you have the maximum potential energy, and at its equilibrium point is when you have the maximum kinetic energy. And we'll do problems, and you'll see them as well. The kinematics of oscillation. Some equations we have to know. Period is the number of seconds per cycle. So pretty much a period is how long it takes for something to complete a cycle. If we were talking about the Earth, the period of the Earth would be 24 hours, which is equal to the amount of time it takes for the Earth to complete one cycle around itself. Frequency is how many cycles per second. And frequency and period, like we talked about before, are reciprocals of each other. If something has a period of 2 seconds, that means that the pattern repeats every 2 seconds. If something has a frequency of 40 hertz, and hertz is the unit of measurement for frequency, it means that the pattern repeats 40 times per second. And we have another formula here that helps us find the frequency. And this equation was derived from the following equation that was in your equation sheet. If we combine this is the equation that was on your equation sheet here. We'll just highlight it here with some yellow. And if we rearrange the equation, we can derive this equation for frequency. And we can see that the frequency, which is how many times the pattern repeats, is inversely proportional to the square of the mass. So that means that if you were to quadruple the mass that a spring is attached to, the frequency would be half of the original amount. And we'll have some other questions, again, dealing with the formulas and what happens when you double this or quadruple that, and how it relates to the period and the frequency. Also, in retrospect, the period is proportional to the mass. If you quadruple the proportional to the square of the mass, if you quadruple the mass, you're gonna end up having a period that is twice the original amount. Meaning it's gonna take more. The more mass you have, the more time it takes for the pattern to repeat. The simple harmonic motion kind of continued. If we look at some of the equations, when you see the pattern being drawn on the paper, you see that it follows a sinusoidal pattern. We can use the sinusoidal pattern to pretty much calculate that the position in the y direction is equal to whatever the amplitude is times sine times the frequency, angular frequency times time. When you take the angular frequency and multiply times time, you actually get the angular displacement. Remember, angular frequency, even though it's kind of like angular velocity, it's radians per second, and when you multiply it times time, the seconds cancel out and you answer in radians. Because your answer is in radians, if you need to plug this into your calculator, now is when you have to start changing your calculator to radians. When you use this equation, your angle is given to you in radians, so be careful with that. Unfortunately, this equation is only true when at t equals 0, the spring is at its natural length. And we'll talk about the equation that when it's not at its natural length when t equals 0. This is the equation for vertical oscillation, meaning something bouncing up and down. The equation for horizontal oscillation, such as the one in the picture here, how far the spring is moving back and forth, can be found by just doing the x components of it, which x is equal to a cosine angular frequency times time. And then again, angular frequency is equal to the displacement in radians over time, which can also be said as 2 pi over t. Since 2 pi is how long it takes something to complete a pattern around a circle, and t is how long it takes for the period to repeat, you could also calculate the angular velocity or the angular frequency in the same way. And some of the other equations we've already derived. If you have a situation where they don't tell you that the spring did not start at its natural length, you can use the following equation, which is on your equation sheet, that last equation we highlighted that we said was going to talk about, where x max is pretty much your amplitude because it's the maximum your x can be. And this little phi at the end is the initial phase, meaning that where it is on its angle. If if at t equals 0, you're at your equilibrium point, which is right back in the middle, you can say that phi is equal to 0. If, for example, it was at its maximum point, meaning at the top of one of the crests, then phi is equal to pi over 2, because the pattern repeats every 2 pi's, and when you're all the way at one of the crests, you're 1/4 of the way through the cycle. So we'll have to practice that whole unit circle and radians as we get through these problems. So almost done, guys. Last thing to really talk about is vertical oscillation. Again, just kind of touching base on a few things. A vertical oscillation, you're usually going to experience a constant external net force. Constant external force. That external force is usually going to be gravity. When you have something pulling down on gravity, the natural length of the spring is not the natural length you will use. Your natural length is equal to where the length at which the spring, which is tied to some kind of mass, just hangs by itself. So you first have to figure out or look through the problem and find out where that length is. The moment you attach something to the spring is going to naturally come down to a length where it just stays without oscillating. That's going to be your new natural length. Your natural length is when the spring doesn't oscillate back and forth. So when you add a weight to it, it changes the oscillation point. That point is usually when the force constant of the spring is equal to the force of gravity. So if we call that position d naught, which is how far it moves from the spring's normal length when you added the weight, we can find out that the new equilibrium point is equal to the mass times gravity over k, and this is true for whenever there's force of gravity acting down on one. So pretty much when the displacement of the spring is more than the equilibrium point, which will be around here, the force of the spring is greater than the force of gravity. The force of the spring is going to start to slow down the ball in this case, bring it almost completely to rest when it reaches its amplitude point, and then starts bouncing back in the opposite direction. When d is less than d naught, meaning the displacement it's already started to bounce back, the force of the spring is less than the force of gravity, and gravity is going to start to pull the ball down, slowing it down, bringing it to a stop at that highest point, and then making it come down again, and it's just going to repeat over and over and over again. And we have that frequency equation that we have on our equation sheet, which is true actually for any of those situations. So it's not just always true for vertical oscillations. And we'll stop right there, and then in the next video we'll do a bunch of problems and kind of make sense of all these equations we have in front of us.